Okay, good morning, everyone. Welcome to our webinar this week. Today, we're going to be talking about Spectral Whispers, a spectroscopic investigation of the dead. So today, we're going to be covering forensics using spectrometers or spectroradiometers. And we have a guest speaker here today, Sarah Zapico, and I'll be introducing her in a later slide. But thank you very much for joining us this morning. So I'm going to briefly introduce Spectral Evolution. We're the leading manufacturer of UV-Vis NIR spectrometers and spectroradiometers. We've been around since 2004, and we're built and manufactured, located in Haverhill, Massachusetts, so the Boston area. Our primary applications are in hyperspectral applications, remote sensing and vegetation, mining and geology, as well as photonics and calibration transfer. And so here on the left, we have our NaturSpec Ultra out in the field scanning soil samples. But today we're going to be focusing on what Sarah Zapico has brought to us today, which is forensics using a spectrometer. So Sarah is from the New Jersey Institute of Technology. She is a PhD as an assistant professor in the Department of Chemistry and Environmental Sciences at New Jersey Institute of Technology. She is also a research associate at the Smithsonian Institution. She received her PhD in biochemistry with a focus in biomedical sciences from the University Institute of Oncology of Principado de Asturias in Spain, and her master's in forensic anthropology and genetics from the University of Granada in Spain. After that, she was a postdoc fellow at the Smithsonian Institute and an associate at the forensics unit from the International Committee of the Red Cross in Geneva, Switzerland, completing her postdoc training with other visiting scientist positions before coming to New Jersey Institute of Technology. Sarah was the graduate program director of the Professional Science Masters in Forensic Science at Florida International University. Her research interests focus on the application of biochemical techniques to forensic science issues like age at death, estimation, and the determination of post-mortem interval with the implications in aging and biomedical research. Thank you very much, and I'll let Sarah take it away. There we go.
Screen. Okay. Can you see my full screen? Yeah.
Looks great.
Okay, perfect. Thank you. Thank you very much for this opportunity. First, I'm going to talk about a spectroscopic investigation of the dead in two different aspects. First of all, if you are not familiar with forensics, I am sure you're thinking about forensic anthropology is this. Actually, this is what Israeli. This is myself going into a crime scene in New York when I was visiting scientists. So actually, forensic anthropology is the application of the knowledge and techniques of human skeletal biology to medical legal issues. So yes, we work on the examination of skeletal remains to assist in their identification and interpretation of what happened to them. And this is what I'm going to talk about today. In this interpretation of what happened to them, we need to talk about the post-mortem interval or time since death. Really, what it means is how long ago the person died. And it's not as simple as it looks like. A body after death passed by different processes from fresh to skeletonized remains. In terms of fresh, normally is from 1 day to approximately 1 week after death. And these are the typical things that I am sure, watch in any TV show, crime TV show or movie. the rigor mortis, the stiffness of the muscles, the livor mortis, the lividity, and the algor mortis, the decrease in body temperature after death. And for example, you have here an image of CSI Miami, where the medical examiner is going to take the temperature of the body to determine how long ago died, based on the decrease in the temperature. And here you have the original Death on the Nile movie, in which the maid has something in the hand. And Poirot tried to take it, but the rigor mortis, the stiffness of the muscle, is already set up. So it was difficult for him to pick up. So in this first stage, it's more or less easy to determine the post-mortem interval, or how long ago the person died, based on these parameters. The problem is when we face skeletonized remains. And in skeletonized remains, as you can see in this table, the BMI could be from several weeks to months after death. And also, you have to take into account that there are different environmental conditions and other things that could affect the decomposition. The first one is the temperature. As I always said, it's not the same body decomposed here in New York, for example, than in Miami, where I was before. So the temperature, the humidity will speed up the decomposition, and we have skeletonized remains earlier. The access by insects also could be a factor to speed up this. If the body is burial or not, the scavenging, so if the animals are going to eat the remains, also if there is trauma as well, in the remains, the humidity, as I said before, the body size, so also internal factors of the body, if there was embalming of the remains, the clothing, also they could prevent the access of insects and others, and the substrate. So for example, the soil, acid or basic. So all these factors contribute to the decomposition, and could also be a problem when we try to determine how long ago the person died. So what's the problem? An accurate BMI estimation, particularly in skeletonized remains. So in this field, when we have skeletonized remains, previous studies were based on imaging techniques or lighting techniques like spectroscopy. But these previous studies were based on X-rays. So here we have the light spectra. So these techniques were based in X-rays, like when we go to the doctor, more or less the same, I will say. And then infrared, which is, as you can see, between the radio waves and the visible light. Why these spectroscopy lighting techniques? Because the bone internal structure changes over time. And this, how the bone react with the light, can be studied based on that, based on these X-rays or infrared. But what is the problem with these techniques? Are invasive, so requires the destruction of the sample. Also, we need a lab to be performed, and requires to be carried out by expert personnel. And because of all of this, it's not possible to translate to the field. So it won't be possible to determine, going to the field and determine on the field if the body is, for example, historical or is of forensic significance. So what will be our solution? Using ultraviolet visible near-infrared spectroscopy. And here again, we have the light spectra, but the idea is to use only these ultraviolet visible and near infrared to analyze, to determine the BMI. What will be the advantages? Quick analysis and quantification of how bones reflect the light over time. Also, we can create libraries to determine the BMI based on comparison of this parameter. And it's portable. So we can go to the field and determine if the remains are, for example, historical or are recent. So our objective in this first part was the application of ultraviolet visible near-infrared spectroscopy for PMI estimation in skeletal remains. And for that, we use the natural ultra spectroradiometer, and we use 50 skeletal remains from the skeletal collection from Mercyhurst University in Erie, Pennsylvania. And this one were a mixture of forensic cases and donations with PMIs ranging 1 to 20 years. Also, we have anatomical specimens and for a forensic case. And what you have there is one of the skeletal donation, sorry. Then this one here, you have an anatomical, the anatomical specimens and the forensic case. What were our methods? So we used the contact proof, the big proof. And we scan the head of the femur, the shaft of the femur, and the condyles of the femur. And from the head, we scan the parietals, the frontal, and the temporal that you won't see, but it will be below the parietals, and also the teeth. And as I told you, we use the contact proof mostly for the large areas. For the teeth, we use the mini proof. What were our results? So here I show you only a representative for each PMI, but you can see here we saw differences between 20 years, which the reflectance is higher than 1 year PMI. When we analyzed the anatomical specimens, we didn't know really how long ago were they died. I mean, they were actual remains, but we saw that the anatomical specimen, one of them paired with the 20 years PMI, and the other one was between the 20 years and the 15 years approximately. But the best results, I will say, and this was exciting, was with the forensic case. I haven't told you that, but they suspect that the forensic case was not a forensic case, was a historical case. So actually, these are our results. So this was the forensic case. So the spectra changed completely, and the one below is the 20 years. So this could suggest that this is really a historical case, not an actual case. So based on the difference between the 20 years and this spectra. So it kind of, this confirms what they suspect, that really what they have, it was a historical case, possibly from the Civil War in the United States. So I think this result was amazing and really useful in terms of the forensic case. So based on these results, the next step was to create libraries based on the ECID. So we created libraries based on the 1 to 20 years PMI scans. And here I will show you only the mid-shaft of the femur, but the results were similar in the other parts. So here in the ECID, I put a 17 years old sample, and based on our library of PMI library, the highest correlation was with another 17-year-old sample and the anatomical specimen. And I hope you remember from the previous slide that, yes, one of the anatomical specimen per approximately around 15, 17 years old. Then the next step in this library, we decided to create regions. Why we decided to create regions? Because in other techniques, the FTIR, the X-rays and infrared, they analyze ratios based on different wavelengths. So we create here these regions to see if, based on the regions, our matching was better. So here you can see that in this case, with the same sample, it only correlates, or the highest correlation was with another 17-year-old sample, not with the, in this case, with the one of the anatomical specimens. With the same with a 6-year sample. And here we realized that the highest correlation with the regions was with another 6-year-old sample and 8-year-old sample. With the regions, the highest correlation was with another 6-year-old sample and 4-year-old sample. So we are not sure about the if the regions really contribute or not to this matching. We think that it will be better to compare the full spectra, because as I told you, these regions were based on ratios that people use in infrared, infrared mostly, and because these are ratios, so it will be 2 of the wavelengths ratios mostly. So to our mind, I think it will be better to compare the full spectra. So conclusions of this part: the application of ultraviolet visible near-infrared spectroscopy to bones with PMIs between 1 and 20 years old show different patterns in the bone reflecting light over time. This light range was able to distinguish between historical skeletons versus model skeletons. And it was possible to create libraries to predict the PMI, though more data should be collected from other skeletal collections with broader PMIs and different environments to assess the potential influence of these factors and develop a complete and more accurate library. With the current data, different parameters will be calculated to evaluate different bone characteristics with the PMI and develop statistical formulas to predict the PMI. So this is our future work from this part. Also, while I was at Mercyhurst, we decided to analyze more things. We keep with the assist with the identification of human remains and interpretation of what happened to them. Here it was both aims. And we thought about burned human remains. When a corpse is subjected to fire, depending on the temperature and time of the fire, you can have different burning. So for example, as you can see, this is lance burn. I would say intermediate and completely burn almost. So what is the problem here? So with the time, there is a change, with the time and temperature, there is a change in the macroscopic form or the bone and teeth. In this case, you can see here, this is a project that we did a few years back, that we set up temperatures and time. So we burn teeth with from 100 degrees to 700 degrees between 1 minute to 15 minutes and analyze the changes in the macroscopic parts of the teeth. And also we assess up until which temperature and time we were able to get DNA. So in the first temperatures and times, as you can see, you can almost don't see if the teeth were really burned or not. When we increase the temperature and time, 710, 15 minutes, you can see also the teeth were completely burned, and also they broke because of the effects of the fire. So from our results with the DNA, we realized around 315 minutes or 401 minutes, we were able to get the DNA. But the problem is when we face these remains that don't look like burned, but actually they are burned, if we know if we can extract the DNA. So what's the problem? The identification of burned human remains. Evaluate the possibility of obtaining high quality DNA. And you can see also previous studies here, some people trying to get DNA from burned remains use different DNA extraction methods, alternative tissues or source, and new technologies. But also they use imaging techniques like infrared or others to assess the DNA damage. So based on that, we decided to see if using ultraviolet visible near-infrared spectroscopy, we could assess the temperature at time exposure of the remains and then correlate with the DNA, which will be the second part, which is not here. So for that, again, we use the natural spec ultra spectroradiometer, and we use first control teeth, not exposure, and then teeth exposure to fire from 100 degrees to 600 degrees in this case, 1, 5, 10, and 15 minutes, again from Mercyhurst University skeletal collection. And I don't know if you see well, but in the first teeth, let me put. Okay. This one are the lowest temperature and times, and you can see, you almost don't see that they are really burnt. And here in this case, we, if the tooth was complete, we scan two regions: the crown, which is the part of your tooth that you touch with your tongue, and the root, which is the part of your tooth that is covered by the gum. But if the tooth was completely burned and broken, we scan only the whole tooth here. And in this case, because of the size of the teeth, we use the mini proof. What were our results? And this is what I told you before, that the mess, but this one here, I need to show you the mess to point out different things. So here you have the control tooth, and you can see with 100 degrees and 1 minute, we were able to detect that the tooth was really burnt. The problem, or I would say it's not the problem, because you can see physically, like around 500, 600, really the spectra were very similar. With temperature at times 500, 600, the spectra were almost a flat line, really low, as you can see here. Again, we try to do libraries with the ECID based on our teeth with all the temperature and times. And here we have a 100 degrees, 1 minute, the crown, and we see it match with the highest correlation with another crown, 100 degrees, 1 minute. And here with the same, from the same tooth, 100 degrees, 1 minute, the root. And again, the highest correlation was another root, 100 degrees, 1 minute. Then the problem, I would say the problem, but we're more interested in this case in the first temperature and time, so we're fine. This is what I meant with the flat line. So this is the 500 degrees, 10 minutes. So it was the whole tooth because of the because it was almost broken. So you see, this is the flat line in the spectra. And then this, the highest correlation match with another 500 degrees, 10 minutes, and 600 degrees, 1 minute. So in the highest temperature and times, it was difficult to distinguish between the temperatures and time. So from, I would say, for 500 up. So conclusions for and future work from this part: ultraviolet visible near-infrared spectroscopy was able to detect burnt teeth with the lowest temperature and time exposure, 100 degrees, 1 minute, even if externally teeth did not show any signs of burning. High temperature broke the teeth, also affecting the differentiation of temperature and times based on the reflectance. This points out the potential of these techniques to evaluate burnt teeth and select the appropriate sample for DNA extraction. And again, our future work aims to expand the number of teeth samples and extend to bones subjected to different temperatures and times. And with this, I would like to thank you first, Mercyhurst University, for letting me use the collections, Dr. Joat Serias Garriga, Luis Cabo Perez, and Dr. Denise Dirman, and the students Sydney Carson, Chenoa Goods, and Graciela Duran Ortega just graduated with her master's, and Spectral Evolution partnerships for research partnership for innovation, and Mackenzie and Nicholas for their help and patience during the process. And with this, thank you so much for this opportunity again. And if you have questions now or later, I will be happy to answer. Thank you so much.